Hello and welcome to our second to last main topic, I'll call it. Let me just get my stuff set up. I guess we don't need this right now. We're going to start some slides. Our topic on Polyhedra. Come on, PDF. Drag you over. This PDF as big as it can be. Let's move it up. Maximized. Oh. As soon as I go too close to the edge, right, it just snaps. Just snaps. Okay. Polyhedra is our last topic. Second to last, sorry. Well, the last one's sort of connected, to be honest. Last big topic, if you will. Yeah. Where we are essentially extending the polygon concept to three-dimensional shapes, essentially. Now, just like before, we are going to restrict ourselves to have as much structure and as simple an environment as possible to get on top of this concept and have an introduction. Things are always much, much more complicated, but that's not necessarily our goal, right? So we want to focus on what I call convex shapes. Now, the idea of convexity is this rounded idea that I have roundish shapes. I don't have shapes with indentations like a little Pac-Man type. More formally, that is defined as a shape is convex if I can take any 2 points anywhere in the shape, and when I connect them, everything on that line is inside the shape as well. So if I look at some examples, take any 2 points, not just this line, any points, could be any line through the shape. It can't exit and then enter the shape again. That is a more formal way of just saying intuitively, I have a roundish shape, no indentations. Because as soon as I allow that, we did say that these bottom ones are technically polygons, but they're hard to work with for an introduction. So we ignore them by requiring the shapes to be convex. Now, of course, circles and things like that are a little bit fancier, are technically convex as well. So we have this idea of convexity just to get us started in the right direction. All regular polygons are convex, which is why we look at them for our introduction on two-dimensional geometry, but many other shapes as well. Now this concept continues when I go into 3 dimensions, that I want to look at these roundish shapes. There's still going to be a lot of room for discussion, even by restricting myself to these convex shapes, so don't worry. But it excludes a lot of more complicated shapes, especially in 3 dimensions. Don't want to look at those at the beginning for my introduction. So the concept is the same. If I draw a line through the shape, it can't exit and enter the shape again. That will only happen when I have this some sort of indentation and I'm trying to avoid anything like that. But you can think of it as a round, bulging shape, if you will. No indentations of any kind. So that's what we will restrict ourselves to look at just for simplicity. So now when we extend the concept of a shape to 3 dimensions, we don't just have vertices and edges, we also have faces of the 3-dimensional shape. So our edge is still where faces meet each other in an edge, and where edges meet, it forms a vertex. So now we have 3 words that we want to be comfortable with. Vertices, edges, faces. I want to go slow enough. We're not in a hurry. I've allowed 4 days. We might not use all 4 days. We'll just take our time and go at a pace that is comfortable. So, a polyhedron, just like polygon came from the words poly and gon, many, many sides. Here we have polyhedron coming from poly meaning many and hedron meaning face, many faces. So that's an appropriate name. The plural is polyhedra. So that is now the extension of polygons. 3 dimensions, we have 1 polyhedron or many polyhedra, depending on what we want to say. So we have our familiar cube. Cube, you can see it, ice cubes, and many other things. Familiar shape. First one we might think of. But there are many others. And the faces are now polygons, different polygons. In the cube, I have square faces. If I look at a brick, I have rectangular faces maybe. In this one on the right, I have triangle faces, but I still have faces, edges, and vertices coming together to make a convex 3-dimensional shape called a polyhedron. Right, so now we're extending our knowledge from 2 dimensions into 3 dimensions. Now there are many ways to refer to a specific polyhedron. One way, and we're going to come back to this a little later, is by somehow representing the 3-dimensional shape on the screen, on paper, or whatever. So here you can see by the way it's drawn, some shadows here and the perspective. It's trying to give the impression of a 3-dimensional shape, which it of course is. But if we think about this actually being like a cereal box or something, and we cut it open and fold it flat, then we get a reference to the same shape, still the cube, but sort of folded out, and we call that a net. This on the left, this is sort of the process of folding it up or out. The net is now sort of a 2-dimensional representation of that cube. Now nets in truth can get very complicated once they step away from the cube or a very, very basic shape. So I want to be aware of the concept of a net because it is in the elementary school curriculum. But there as well, we mainly stick to like cereal boxes and stuff, like where you can actually go get a cereal box maybe from home, bring it into school. Let's cut it out and let's fold it out. And let's see how this folded out net is related to the 3-dimensional shape. So it's another way, technically the more precise or proper 2-dimensional representation of the 3-dimensional shape. because here I'm relying on the viewer's interpretation of my drawing, which we saw with things with art by Escher and things like that. Optical illusions are very much a danger. So the net is the actual two-dimensional representation of that polyhedron. And we get it by folding it up to a three-dimensional shape or folding the three-dimensional shape out by cutting along some of the edges. So hopefully, because we're just staying with the cube, you can look at this net and imagine folding it. Now, there isn't necessarily just one way to make, to go from a net to the cube, for example, or there isn't just one way to cut this cube along some edges and fold it out. There are actually many. I'm going to come to that picture in a second. How many different nets could there perhaps be of just a simple cube? There are quite a few. Quite a few. Some of them are maybe less obvious than others, but this first, which one did we see? Oh, this one, this bottom left one. Look at the top one. That to me is fairly easy to imagine as well. I'll fold the middle all the way around and then fold the sides up to make a cube. There are many other ways I could have laid this out into one connected piece so that when I fold it back, I'll make a cube. No overlapping, no gaps or anything. So the idea of a net is or can be quite complicated once I step away from very simple polyhedra cube, right? We have a good sense for a cube. Once I step away, the question in general of how many nets are there for a specific shape, that is a very, very difficult question. Or if I give you just a shape that looks like it could be a net, like laid out, to confirm that actually creates a proper polyhedron, no gaps, nothing missing, it fits perfectly, that is a question that's not even fully answered in general. See here, everything looks okay on my end, stream, but remember that I am recording a backup, so if on your end it just seems strange, then be sure to watch the backup so that we don't miss anything. So here's a picture of the other one that we showed here with triangle faces, where this is used. This is done on a computer because it's so hard to even imagine, for me at least, that this bottom right shape or layout will be a net for this polyhedron. That's very hard, or near impossible for me to verify that these two are the same, are different representations of the same shape. So the concept of a net gets very complicated very quickly. Uh, and I could ask how many nets are there? Given a net, can it make a polyhedron? Very, very difficult. Very difficult. So stick to a cube or a very, very basic shape, even though this polyhedron seems to have a lot of structure, just nice simple triangle faces. When I talk about the net, it can be quite a difficult thing. So I want to be aware of nets, but I don't want to step away from a very basic shape. Because this is just our introduction, right? The whole few days that we'll spend on this, still just an introduction. Drop in the bucket of a very, very large and not completely known bucket. Okay, so the concept of a net. Now, oh, I'm going backwards. That's why I'm so confused. Why am I seeing screen pages that I've seen already? There we go. Okay. So just like we've done in the polygon case, what is the simplest polygon we could make? That is where all the sides are the same, all the angles, everything is the same. We're going to do the same thing for polyhedron, for polyhedra, that's the plural, where I take one regular polygon for all the faces, copies of that polygon. In the case of a cube, of course, the faces are all the same square. Assembled in a way, in the same way around each vertex. If I look at the cube here, 3 squares come together at one vertex. 2 faces come together at an edge. And no matter how I rotate and spin this cube around, at every vertex, the same thing happens. Okay? So I want as much structure as I can to try and better understand, uh, try and have an easier path through this introduction. So this was probably first investigated by the Greek philosopher Plato, and we still call these regular polyhedra Platonic solids. Now, for the cube, we can see that ice cube, things like that. It's not hard to imagine, and we sort of grew up with that concept, so it's fairly intuitive. The question becomes, how many are there? Now, I won't show that slide because there's a lot of words, and we'll try and explore this first. The question that he had as well, how many of these regular polyhedra are possible? Let's have a look. Let me move my slides. Just get myself organized here and zoom. Check that my screen is showing well. Okay. So let's just see what makes the cube work. So regular polyhedron. So now first, of course, I have to understand, what do I mean by regular polyhedron, right? I don't want to move on if I'm not quite ready to move on. I want a regular polygon and one regular polygon, to copies of it to make all the faces. And I have to sort of glue those faces together in the same way everywhere. So I have my familiar cube. Let's draw a not great representation of the cube. Not my best work. It looks a little flat, but it's a cube. I can have some dotted lines there to show the background as well. So now the question is, why does the cube work? Well, if I focus on what happens at this vertex that's sort of looking at me, and I ignore the back of the cube, and I cut the one of the edges open. Make it pink. I cut this edge. I cut along this edge. And then I fold it out to look at that part of the net. Well, the top face is going to be this one. It's attached to this front face, and then the side one on the right is going to sit over here. When I fold it out, pink edges came from sort of folding this in. Now, it's hard because online format, this net continues in some way. I don't really care too much. But the point here is to go from this portion, at least, of the net, that's my same vertex there that I'm creating, I have to sort of fold in this gap. Fold the gap. I need a gap in 2 dimensions when it's folded flat. Sorry, when it's laid out flat. I need this gap so that I fold it in and create this 3-dimensional shape. That. So first of all, here I say I'll observe that I need a gap for the folding to work. Fold successfully. And I also realized that I'm going to need 3 of these square faces, right? If I just have 2 faces, that's impossible. I'm going to need, in my net here, I'll need at least 3 faces at a vertex, right? The cube has 3 square faces coming together at a vertex. And in this case, each face is a square. Now, the interior angles here are all 90 degrees. Let's say here interior angle 90 degrees. So in the net around this vertex, I have 3 of these angles coming together. Let's say around the vertex. And because every vertex is exactly the same in my cube, I can just look at any one of them, right? Around the vertex, I have 3 angles of 90 degrees, so a total of 270 degrees. And because 270 is not 360 degrees would be a full rotation, that implies I have a gap. Now it seems a little silly to write all this out when I can visualize it, but I can visualize it because it's the cube. And maybe to try and investigate if there are other polyhedra possible, other regular polyhedra possible, I might not be able to visualize it as nicely as the cube. So I'm trying to come up with a requirement outside of my drawing and visualization abilities. So first of all, I need to have a gap that I can fold. If I have everything, if I don't have any gap on the 2-dimensional net, then how do I fold it to make it 3 dimensions? It's impossible. I need a gap. And I need at least 3 faces to come together at a vertex. 2 faces won't actually make a 3-dimensional shape. Might have more, so we'll have to explore that. So when I now look at the cube and its net around this vertex, each face is a square. The interior angle of a square I know from my knowledge of polygons, which means if I have 3 of them around a vertex, let's say here 3 around a vertex, that'll mean I am using, of the available 360 degrees, 270, so I have a gap. So I can use these points to try and discover other possibilities. Again, I'm trying to go slow enough so that we can keep up and understand what is happening. So obviously, though I just need at least 3 faces at a vertex. For the case of a square, if I have four square faces at a vertex, it's not going to work because then I lose my gap, right? Because 4 times 90 is 360. It's not going to work. So let's say here, let's observe 4 square faces. That's not going to work because then I have no gap. 4 times 90 degrees, which is the interior angle, is exactly 360, and then I'm perfectly making a tessellation, but that's not the goal here. I need a gap to be able to fold it. Okay, so as far as a square face goes, it's the cube or nothing. Okay. So I actually want to leave this open so we can refer to these points and go through them for other possibilities. Okay, let me just move down. Check, it looks good. So now what else can happen? Well, let's just start with the simplest polygon that I can use for faces. What about triangle faces? So now the minimum I'm gonna have to put together at a vertex. I'm copying this over here, right? So I want to start with what the connection around a vertex could look like in the folded out net. Well, I'm going to need 3 triangles, right? Let's put them over there, like so. I'm going to need at least 3 triangles. That's the minimum number of faces that need to come together at a vertex. So now I might not be able to visualize the 3-dimensional shape, but that's not a requirement. I'm going to fold this part of the net, which does continue, and I don't know how, not yet. I'm going to fold this together, fold here, but I need to check. Okay, I need at least 3 vertices, 3 faces at a vertex. Good, check. I want to fold a gap, so I better make sure that I have a gap. Okay, so let's double check. So I have each face a triangle, a regular triangle, right? I'm trying to copy this, and I just made this up, so I don't remember the exact order here. Interior angle of an equilateral triangle is 60 degrees. That means I now have 60 degrees, 60 degrees, 60 degrees of my existing faces. So I want 3 to come together around a vertex. So I've used, of my full rotation 360 degrees, I've used 3 times 60 degrees, which is 180 degrees. So when I compare that to my available 360 degrees, I clearly have a gap. But I can't necessarily rely on my freehand sketch here, right? I need to make sure, okay, do I have a gap? I have a big gap. So I can fold that gap and make a 3-dimensional shape. 3 triangle faces coming together at a vertex. Now I'm going to leave it a little bit of a mystery what that shape's going to look like. But theoretically, based on what we've discovered about the intuitive cube, it's possible. All the requirements are met. I have a gap. I can fold over that gap to make a 3-dimensional shape. I've verified it numerically. 3 faces will come together. What does that shape look like? Maybe I have no idea at this stage, and that's okay. We're going to see in a second. Let's try more triangle faces because we see here our gap is quite big, and that's okay, but we have some room to move here. So far, we're only taking up half of the 360 available. So around a vertex, I can maybe have 4 triangles. Now, my triangles won't look very good, but they are there. 1, 2, 3, 4. Equilateral, right? They obviously look perfectly equilateral. I know. So now I'm going to try 4 triangle faces. Let's just make our here. I'm going to try 4 triangle faces around a vertex. Each face is still going to be a triangle, but I can't rely on this sketch. I want to see, is there actually a gap? I want to fold and essentially glue these edges together. Can I even do that? Well, I have to check the numbers. The interior angle is still 60 degrees because I still am working with a face. That's an equilateral triangle. When I now try 4 of them together and I lay them flat in the net, 4 times 60 degrees is 240 degrees. And if I compare that to my available 360 all the way around, I have a gap. So I'm good. I have a gap. So there is a gap that I can fold and make the three-dimensional shape with 4 triangles coming together. All right. So because the triangle interior angle is so small, as long as I come in under 360 degrees to have a gap, I can then fold that gap and create the three-dimensional shape. So 3 worked, 4 worked. Oh, let's keep going. Why not 5? Now I just have to draw this, I guess, a little bit more carefully. There's a triangle there. My wonderful triangles, 1, 2, 3, 5, and I'm hoping there's a gap there. I have to verify. Is there a gap that I can then visualize gluing these two to make one edge of the eventual three-dimensional shape? Well, let's see. Each face is still going to be an equilateral triangle. My interior angle is therefore still 60 degrees, each one, 60, 60. I want to try 5 around, a vertex. Oh, whoopsie, not 50. That will definitely not work. Only 5. 5 times 60 is 300. And when I compare that to my available full rotation 360, yeah, still have a gap. Still have a gap. Very nice. So I will have the opportunity to fold no, there's not it's the gap. I will fold it. I have the space here to fold it and create a three-dimensional shape. Of course, I don't know what the rest looks like, right? Don't know. But every vertex is going to have the same property of having 5 triangles coming together, so we'll worry about that later. Now, you can just look at this and see, hopefully, that if I go further and make 6 triangles to come together at a vertex, that's not going to work because 6 times 60 is 360. Yes, it fits in the tessellation sense, but I need a gap in my net to fold and create the three-dimensional shape. So I can't fit perfectly in the plane. I need to have a gap. Yeah. So there is a strong connection between this and tessellations. I guess this is a little bit more general. Tessellations, we didn't want any gap. We wanted them to fit perfectly, and triangles did work. Here, we want the gap to be able to make the transition to 3 dimensions by folding this. So we have our cube, which was a nice first one because we're sort of used to that. And we have 3 possibilities for how to make a regular polyhedron consisting of equilateral triangle faces by looking at how many of these triangles can come together at a vertex. But wait, there is more. Because the question is, well, how many can we make? So we've established we can't use more triangles. When we looked at the cube, we can't have more than 3 square faces coming together. So the triangles and the squares are kind of done. And by kind of, I mean they are done. So I guess this is number 4. Technically, this is number 4. If I build up in terms of the faces, triangles, did everything we can, got 3 of them. Then go up to a square face, yeah, get the cube. So next up is Pentagon face. That would be the next polygon up, Pentagon faces. Now the Pentagon is a little bit more difficult to draw, I admit. I can actually see my procedure here, right? So now the minimum I can do, I'm going to try to put together 3 pentagons and connect them at a vertex. Oh, that's not bad. Hopefully I'll have a gap so that I can then glue those edges together when I fold it and make my 3-dimensional shape. But I don't know that for sure right now. Let's go through our steps. Each face is now a regular pentagon. I can't freehand a regular pentagon, but they're all going to be regular. They want that structure. Now, if you remember the interior angle of a pentagon, we calculated it. I said you have to be able to do it. It's 108. Now the minimum I have to have, minimum number is 3 to come together around a vertex. Otherwise I won't have anything to fold. 2 just won't work. I'll just fold it flat. I'm trying to create a 3-dimensional shape. So 3 times 108 is, of course, 324. But that's good news because when I compare it to 360 degrees, it means I have a gap. And that's all I need. I don't care how big or small the gap is. I have it. And I can fold over that gap, create a 3-dimensional shape with pentagon faces. I can do it. So there's another one. And we're going to show these in a second. But theoretically, yeah, it's possible. Now I just want to highlight, if I go further, what happens. So I'll just say here, before we go on to hexagons, if I try another one, if I try 4 pentagon faces, 4 times 108 is going to overshoot 360, obviously, right? I'll have over 400. So 3 is the best I can do. Hexagon faces. Well, if I just look at a single hexagon, if I want to glue them together, each face, I just drew it. Why do I have to do it again? Hexagons aren't bad, actually. A hexagon, a regular hexagon. So the interior angle is 120. We've done this. I need a minimum of 3 around a vertex. Ooh, my writing is wonderful today. Which means 3 times 120. That is exactly 360, but that means I have no gap. because we remember that the hexagon, regular hexagon, forms a tessellation. It's a regular tessellation. There's no gap, which means I can't fold it. It has to stay flat. Can't be used to make a polyhedron. Can't be done because there's no room to fold. Gap, no fold. Sad face. And if I go further with larger with larger polygons rather, the interior angle just goes up and up and up. I need a minimum of 3, so I'm just going to drift away further above 360, and I'll have no gap. Actually, I'll have an overlap. It's actually worse than a gap. This one fits perfectly and at least has a tessellation. If I go any further, heptagons, octagons, now 3 times that interior angle, which keeps going up, is just going to drift further away from 360, and I conclude that pentagons are as far as I can go. Okay, but it's important to understand why are there only these 5 regular polyhedra? Why can I not use faces that are bigger polygons? Say it again. If I use other larger, of course regular, polygons, the interior angle just increases. For a larger polygon, heptagon has a larger interior angle. Octagon, larger, and so on and so on. They just get bigger and bigger and bigger. I still need 3, so 3 times a larger interior angle is just going to be further away from 360. And I don't have a gap. I can't come back and create a gap ever again because I need a minimum of 3. The smaller polygons still gives me the opportunity for a gap. So to review, I have the cube. I have 3 triangle faces coming together, 4 triangle faces coming together, at a vertex, of course, 5 triangle faces coming together, and I have 3 pentagon faces coming together. Nothing else is possible. There are only 5 platonic solids. Now I don't really, let me just resize this. Right. Sizing looks good. I don't care about this. We've done this. This is just a very short little description of why there are only 5, and here they are. Here they are. Don't care about these columns right now. About that. What about the picture and the name? So we have the cube here. Cube, familiar, well known, good. When we attach 3 triangle faces at a vertex, we get the tetrahedron. You see here, there's a top vertex, there's a bottom left vertex, there's a bottom right vertex, there's a vertex at the back. For all of them, they have the same structure, 3 triangles coming together. If I allow 4 triangles coming together, it does work, it is beautiful, it is an octahedron. Octahedron. Any one of them, 4 triangles coming together. 5 triangles coming together, that's also possible. I get the icosahedron. A little bigger, more things happening there. The dotted lines are a little distracting, I admit, but there it is. Cube, I just said. When I have my 5 pentagon faces coming together, I get the dodecahedron. Dodecahedron. So our next task is to just explore a little further this set, this collection of 5 platonic solids. I want to understand. This is now the introduction. This is these are the polyhedra with the most structure. First step into this topic. And I want to understand all the properties, explore all the properties of these 5 platonic solids. I need to eventually be able to draw them like these diagrams as well. There are going to be different ways to refer to a polyhedron. It'll have a name coming from Greek words. These are the names, except for the cube, that's a little different. These are the names for these platonic solids. They have nets, but aside from the cube and maybe the tetrahedron, the nets can be very complicated. So we can't really explore much in that direction. It has a two-dimensional drawing of the three-dimensional shape, like these blue ones. And I have to be able to copy this. So over the time that you have available, maybe try and practice some of these. The cube, do that first, and then build up from the tetrahedron. Can I draw the octahedron? Can I draw these 2 more difficult ones? Because I have to be able to eventually. And maybe next time when we're together again, I'll start by drawing these, and then we'll explore their properties and just see where the time takes us. All right, so there's nothing really to practice right now on this other than maybe try and draw some of the easier ones. I find only the icosahedron and the dodecahedron could really going to present a challenge to draw these for these representations. So try and make some progress so it's not too brand new next. All right. Are there any questions this stage? All right, then enjoy the rest of your day and see each other again next time.